All right, this video is going to be the beginning of relativity, and relativity will end up some really weird results. The math itself isn't really all that hard. All right, so first we're going to start off just with something you're familiar with, just like driving a car. You're traveling at 50 down the highway, and a second car travels in the same direction at 60 going past you. It doesn't, from your frame of reference, it doesn't look like he's going 60. As he goes by, it takes a little while for him to get past your car. He's really only going 10 miles an hour faster than you. So his relative speed to you is going to be the difference, or 10 miles per hour. So him going past you at 60 while you're going 50 looks the same to you as if you were sitting still and he's going past you at 10. So when you're going in the same direction, you subtract them to get their relative velocities. If you're traveling towards each other, you're just going to add them. If you're going 50 and he's going 60 this way, if you crash, that's going to be one heck of a crash because it's as if you were sitting still and he's going 110. So when they're going in the same direction, you just add them. All right? So there's an old theory of light and a famous failed experiment. All waves need a medium to travel through. And this is true, we know this. Okay, sound waves need air. As I speak, the air molecules are vibrating against each other, and that transfers the sound from my mouth to your ears. If there's no air, sound doesn't travel. So when they were studying light, early on, they said there's no air in space, so what is the medium? Okay, and they said the medium for air is something that exists in space that doesn't exist here, and they called it ether. All right, now we know that's not true, but at the time that's what they thought. So this is our old theory. All right, so Michelson and Morley, around the year 1900, they wanted to study light and ether. And they devised a way they could measure the speed of light. All right, and we're going to call the speed of light c. And as the Earth is going around the sun, it has a velocity v. And right here, okay, they're moving towards each other. So they expected their measured velocity if they're going in the same direction, we're just going to add them together. It would equal v plus c. And then down here, when they're moving in the same direction, just like up here, if they're moving in the same direction, we subtract them, they expected their measured velocity to be c minus v, the difference. And they found out something that they didn't expect at all, is that the speed of light was the same, independent of the motion of the Earth, or just basically independent of any motion. What they actually got is the speed of light is always c. So that would be kind of strange. So here, when you're going 50, somebody passes you at 60, you're going to measure the difference to be 10. But if you're going 50 and a beam of light goes past you at the speed of light, you measure exactly the speed of light, not the speed of light, minus 50. No matter how you're moving, you always get the same value for the speed of light. It's a constant. And they didn't know what to make of it. And Einstein comes up with special relativity. And special relativity deals with things traveling near the speed of light. It's called special relativity because it only works for objects in an inertial reference frame. And that means they're not accelerating. They have to be at a constant speed. But when he started thinking about what light would do in an inertial reference frame, and the fact that the speed of light had to be constant, he ended up with some really weird results. And here's one of them. He said, imagine a train traveling at a velocity v. There's a tall pole on the train, and you're going to shine a flashlight from the bottom of the pole to the top of the pole. All right? And this guy, O prime, this is the moving observer. He's on the train, all right, or the prime observer. And then this down here is the stationary observer. Okay? Well, to the guy on the train, if he throws a ball up and then catches it, to him the ball just goes straight up and comes straight back down. But to somebody over here, the ball looks like it does this. Similarly, for the light beam, when it goes from the bottom to the top, it just goes this way for him. So he says, oh, it went just the height of this, I'm going to call it d prime, and the time it took was t prime. All right? But to the observer over here, it started here, and as the train moved over, it didn't end till over here. So he says, no, the distance is d, and the time is t. Right? So we're using this equation. Since we're at constant speed, we can use velocity as distance over time. And this guy says, well, my speed of light is going to be d prime over t prime. I'm just going to take that distance divided by that time. I'm going to get the speed. It's for the moving guy. For the stationary guy, he's going to say, I'm going to measure the speed of light, and there's going to be this distance divided by that time. So far, everything makes sense. But since speed of light is constant, C and C prime are the same. So I can set these two things equal to each other. D over T is equal to D prime over T prime. Everything so far makes sense. Since D is greater than D prime, right? This distance is bigger than that distance. For this to be true, if this is bigger than this, for these two fractions to be equal, T has to be bigger than T prime. Okay? And here's where it gets a little bit weird, because we always think of time as being kind of constant. 10 seconds is 10 seconds. But the time measured by the moving observer T prime is less than the time measured by the stationary observer. So if the stationary observer says, okay, it took 4 seconds, the moving observer is going to get a smaller time. He might only get 3 seconds. And it's not that either one of them is wrong, okay? That's what their watches are actually saying. The stationary observer's watch went through 4 ticks. The moving observers went only through 3 ticks. This one is actually, his clock is actually moving slower than his clock. If he could see it, to him it would look like, to the stationary observer, it would look like the moving observer's clock was going slower. And everything on that train, time is slowed down, and everything is going to be moving slower. So time slows down for the moving observer. Now, we don't see this because we're not going close to the speed of light. So time slows down for us, but if we're moving, but very slightly. But for things that are going really fast, close to the speed of light, this can be observed. Now, to get at the equation that we're going to be using for it, I'm just going to redraw that picture. So this distance here, I'm going to rearrange this equation. Velocity is distance divided by time. I can rearrange that as distance is velocity times time. So that distance is going to be c times t. This distance was d prime. It's going to be c times t prime, because this is the light going at the speed of light for a time t covers a distance t. All right, now remember the train was going, so we'll call this distance the train went. It was going at velocity v time t. All right, now if I take a look at this, this is a right triangle. They're related by the Pythagorean theorem. So I can just say d squared is d prime squared plus d train squared. And then I'll plug in the c's and the t's, and I get c squared t squared equals c squared t prime squared plus v squared t squared. Now I'm going to solve this for t prime. I want to know what t prime is going to be. So I'm going to solve for this by subtracting from that from both sides. So I'm going to get c squared t prime squared equals c squared t squared minus, so I'm subtracting that, v squared t squared. All right, now I'm going to divide everything by c squared. So divide by c squared, and I get t prime squared is equal to t squared minus v squared over c squared t squared. Okay, now we can factor out t squared here. So t prime squared is equal to 1 minus v squared over c squared, all of that times t squared. Then take the square root, and I get t prime is equal to square root of 1 minus v squared over c squared times t. Now, looking at this number here is always going to be less than 1 because it's 1 minus something, okay? So t prime is always going to be less than t. Now, it only is important if v is like close to c. For a velocity of 50 miles an hour, 50 miles an hour divided by, speed of light is 3 times 10 to the 8th meter per second. This is going to be very small. So it's 1 minus almost nothing is going to be 1, and I get the same value. But if v becomes close to c, then we notice it. All right, so we have 2 twins. At the moment of the birth, they're separated. One is put as a spaceship that travels at 0.8 c, and we're going to have all of these in terms of c, because it makes the math a whole lot easier. This would be 0.8 times 3 times 10 to the 8th, so 2.4 times 10 to the 8th meters per second. But you don't need to know that, just 8/10 the speed of light. And the other one stays on Earth. When the twin on Earth is 20 years old, how old will the twin on the ship be? So we're going to draw the guy on the Earth. He's going to be my observer. because he stays stationary, and the one on the ship that has a velocity of 0.8 c, he's going to be O prime. He's going to measure a time t, and he's going to have a met time t prime. So 20 years went by for the person on the Earth, and we want to know how much time went by for this guy right here. So these seem kind of confusing, but they're really straightforward. We're just going to be plugging into this equation. All right, so t prime is what we're looking for. It is equal to the square root of 1 minus 0.8 c squared over c squared, and that's going to make the c's cancel. And then t was 20. And you don't have to show that c step if you don't want to. Then t prime is going to equal the square root of 1 minus 0.8 squared is 0.64 times 20. T prime is going to be square root of 0.36 times 20. So t prime is equal to square root of 0.36 is 0.6. So t prime is going to be 12 years. Okay, so when 20 years goes by for the person on the Earth, only 12 years went by for the person who was moving. So even though they were twins born at the same time, when this guy's 20 years old, this guy's only 12 years old. Okay, now, it doesn't mean that he's going to get more life. Let's say they both live to be 100 years. This guy will be 100 years old when this guy is 60 years old. It's the same ratio. Okay? But if they both lived to be 100, he didn't get more life. He died when this guy was 60. This guy lived to be 100, but he didn't get more time. His time just went slower. Now, there's a thing called a twin paradox. All right? What if we did the same calculation from the perspective of the twin on the ship? So the twin on the ship says, okay, I'm sitting still. And the Earth is moving. Because to yourself, you're always sitting still. So if he does the same math, he says, when I am 20, the person on Earth is 12. Because he's the moving one. His time has to go slower. So this gets really weird. The person on Earth says, I'm older. The person on the ship says, no, I'm older. Well, who's right? And it turns out the twin on the ship is wrong. In order to get traveling this fast, he had to speed up. So he was not always at a constant speed. Okay, so it's not an inertial reference frame. So he, the moving twin, is younger.